In the rapidly evolving landscape of artificial intelligence art generation, there are documented cases where the technology produces unexpected outputs that challenge our understanding of these systems. One such case that has generated significant discussion in both art and AI research communities is that of Loab, described as an unsettling female figure with red cheeks, disheveled dark hair, and hollow eyes that emerge through a specific AI image generation technique. Welcome to Vanishing Threads. Today, we examine the documented case of Loab and explore the technical explanations behind stable patterns in AI image generation systems, where the mathematical engines of these technologies sometimes produce unexpected results that warrant scientific investigation. The story begins in April 2022, when digital artist Supercomposite, whose real name is Steph Swanson, was experimenting with the negative prompt feature in an AI art generator. This feature essentially tells the AI what you don't want to see. In a curious test, Swanson input the text string Brando -1, a nonsensical negative prompt that the system would have to interpret without clear direction. According to Swanson's documentation, the system produced a logo-like image featuring the words Digita Pentix, which bore no obvious relationship to the prompt. Intrigued by this output, Swanson then ran a negative prompt of this logo image itself, essentially asking the AI to generate what would be considered the opposite of this abstract logo in the system's latent space. Swanson reported that this process resulted in the first appearance of what she named Loab, an image of a woman with reddish cheeks, dark hair, and what she described as an unsettling gaze. What Swanson found particularly notable was what occurred in subsequent experiments. According to her documentation, when she continued to use this Loab image in combinations with other prompts, the AI appeared to maintain certain visual characteristics across multiple generations, with the system often placing these features in disturbing contexts, despite no explicit prompting for such content. What attracted attention from AI researchers was Swanson's documentation of what appeared to be unusual pattern stability. AI image generation is typically understood to demonstrate significant variation between outputs, even with identical prompts. However, according to Swanson's documentation, certain visual elements remained consistent across multiple generation attempts. "I was completely shocked," Swanson wrote in her technical documentation. "Every time I used the Loab image as input, similar characteristics would appear in the output, often in increasingly disturbing contexts. It was as if the AI had somehow formed a persistent representation of certain visual features." Swanson documented experiments where she varied prompt strength, combined the initial image with different concepts, and reportedly used different AI image generation systems. She reported that in many cases, certain visual elements remained consistent, specifically characteristics like red cheeks and dark hair that she had come to associate with the Loab image. This reported consistency is what drew technical interest from AI researchers studying pattern stability in generative systems. Swanson's documentation of this pattern stability prompted discussions among AI researchers about how these systems organize their internal representations, the so-called latent space, where concepts are mapped in high-dimensional mathematics. While researchers have not verified the specific Loab case with access to Swanson's exact methodology, the general phenomenon of stable regions in latent space has been documented in AI research literature. Researchers in cognitive science and AI ethics at institutions like the University of Toronto and the Schwartz-Reisman Institute for Technology and Society have examined how these cases can be approached from a technical perspective. Published analyses in peer-reviewed journals emphasize that pattern stability in generative AI systems does not indicate consciousness or intent, but rather reveals how these systems create complex associations between concepts that aren't always transparent to human observers. To understand the technical context of Swanson's claim, we need to examine how diffusion models, the class of AI behind most modern image generators, actually work. These systems are trained on billions of images from the internet, learning to recognize patterns and relationships. When given a prompt, they navigate through their latent space, essentially a multi-dimensional map of concepts, to generate images. The negative prompting technique that Swanson described in her documentation can influence which regions of this mathematical space the AI explores during image generation. Professor David Bao of Northeastern University, who specializes in understanding the internal mechanisms of neural networks, has conducted technical research on interpretability in generative models. His published research papers document how these AI models compress the visual world into a mathematical space where similar concepts are positioned near each other. According to his technical publications, techniques like negative prompting can potentially identify stable points in this latent space, though his work emphasizes that rigorous verification procedures are necessary when studying these phenomena. The mathematics behind pattern stability in AI systems remain a subject of ongoing research. In diffusion models, images are generated through a process of gradually adding and removing noise from random patterns, guided by what the model has learned about visual concepts. Research papers by leading deep learning pioneers, including those from Dr. Yoshua Bengio's lab at Mela, have documented how stable attractors can emerge in latent space. These published works describe mathematical regions where certain visual concepts may be disproportionately reinforced through training data distribution patterns. This technical research helps contextualize how persistent patterns might theoretically emerge in these systems. Cases like the one Swanson documented are of interest to AI researchers because they weren't explicitly programmed. They potentially represent emergent properties from the system's learned associations. Dr. Aaron Hertzman, principal scientist at Adobe Research, has published several technical analyses about emergent properties in generative AI systems on the Adobe Research blog. His published work examines the complexity of these models and the difficulty in predicting all possible outputs. According to his technical publications, researchers have observed patterns in generative systems that function similarly to mathematical strange attractors in latent space, which can influence multiple outputs in consistent ways. Pattern stability in AI systems has been documented in various contexts beyond Swanson's Loab documentation. For instance, in documented observations from 2022, some Midjourney users reported encountering what they termed the Eggman, described as a bald figure that would appear with certain architectural prompts. These user reports, while not formally verified through scientific study, align with known technical properties of diffusion models. More rigorously documented, early versions of DALL-E demonstrated a measurable tendency to generate distorted faces with specific prompt patterns, a technical issue that OpenAI engineers specifically addressed in subsequent versions through published technical updates. In research published in peer-reviewed AI journals, pattern stability has been systematically studied. AI researcher Catherine Croson's published work in the proceedings of the IETE Conference on Computer Vision and Pattern Recognition documents architectural patterns that emerged with certain negative prompts. Her research methodology involved testing specific prompt patterns related to architectural styles, which revealed how systems could consistently generate structures with recurring visual elements across multiple runs. The published findings demonstrate how these AI systems can form stable associations between certain inputs and output patterns, providing verifiable examples of pattern stability in controlled experiments. The most rigorously documented research on this topic comes from the Max Planck Institute for Informatics, whose peer-reviewed paper, Persistent Visual Elements in Diffusion Models, catalogues specific visual elements that consistently appeared in generations despite not being explicitly prompted for. Their 2023 publication methodically identifies and analyzes these recurring patterns across controlled experiments with multiple AI systems. The technical AI research community refers to these verified cases as latent space anomalies or emergent patterns. Unlike conventional software bugs that result from coding errors, these patterns emerge from the statistical properties of the trained model. They reveal important information about how AI systems organize concepts in ways that may not align with human expectations, providing valuable insights into the behavior of these complex systems. Swanson's documentation of the Loab case gained significant media attention after she published her findings in September 2022. The story spread across social media and was subsequently covered by technology publications, including The Verge, Ars Technica, and MIT Technology Review. These publications primarily reported Swanson's claims and observations, rather than independently verifying the technical specifics, while connecting them to the broader verified research on pattern stability in AI systems. The striking visuals and narrative presented by Swanson generated substantial public interest in the technical properties of AI image generation systems. Dr. Melanie Mitchell, author of Artificial Intelligence: A Guide for Thinking Humans and researcher at the Santa Fe Institute, has published extensively on pattern emergence in AI systems. Her peer-reviewed publications in the field of AI interpretability analyze how unexpected consistencies in AI outputs provide insights into internal system representations. Her published work in Nature Machine Intelligence examines how generative models build complex, multidimensional conceptual spaces with properties that remain an active area of research interest. The technical AI research community has approached the broader phenomenon of emergent patterns with scientific curiosity. While not specifically validating Swanson's Loab case through independent reproduction, researchers from organizations including DeepMind, Google Brain, and various universities have published analyses examining how generative AI systems develop unexpected stable representations. A 2023 paper published in the journal Machine Learning titled Emergent Phenomena in Generative AI discussed pattern stability as a general property of these systems, referencing user-reported cases alongside rigorously verified research examples. The technical significance of cases like the one Swanson documented lies in how they highlight the complex associations formed within AI training data. While the specific Loab case hasn't been independently reproduced with Swanson's exact methodology, verified research on pattern stability demonstrates that these systems can develop consistent associations that weren't explicitly programmed. In verified cases, researchers have documented how certain input patterns can consistently trigger specific output characteristics, revealing important properties about how these systems organize information. From a computer science perspective, verified research on these systems points to biases and patterns in training data that may not be immediately obvious. Dr. Timnit Gebru, AI ethics researcher and founder of DAR, has published extensive research on how AI training data contains inherent biases. Her peer-reviewed publications document how systems trained on large datasets scraped from the web inevitably absorb patterns and associations from that data, including associations that may produce unexpected or concerning outputs. Her research at DAR specifically examines these data patterns and their downstream effects on AI system behavior. AI safety researchers study emergent behaviors in generative systems as part of their broader work on AI alignment and safety. Research publications from the Future of Humanity Institute have examined how pattern stability in generative models relates to AI safety concerns. Published technical analyses in this field document how both user-reported cases of unexpected pattern stability and verified research examples demonstrate limitations in our ability to predict all possible associations these systems might form. These documented findings raise important questions about deployment considerations in sensitive contexts, as outlined in peer-reviewed literature on AI safety. The mathematical nature of pattern stability in generative AI continues to be an active research area. Teams at DeepMind, Google Brain, and various universities have developed formal frameworks to predict and characterize stable regions in latent space through rigorous peer-reviewed research. Published papers from OpenAI's research team, including those authored by Chief Scientist Dr. Ilya Sutskever, emphasize that understanding these stability dynamics has direct applications for AI safety. These academic publications document how mathematical insights into system behavior can contribute to building safer and more predictable AI systems that behave more consistently with human expectations. In online discussions, some observers have interpreted Swanson's documentation of Loab in supernatural terms, suggesting it represents some form of digital consciousness or paranormal phenomenon. However, AI and computer science experts uniformly reject such interpretations as unfounded. The technical significance of pattern stability in AI systems lies not in any paranormal element, but in what these cases reveal about the mathematical properties of high-dimensional latent spaces and how complex AI systems process and represent information. Research publications by Dr. Emily Denton and other AI researchers at Google emphasize that, while studying stable patterns in AI systems, the observed phenomena are not supernatural, but represent fascinating mathematical properties from a scientific perspective. Their published work on latent space representations documents how these patterns provide insights into the mathematical landscape these systems navigate, a landscape created through training data and algorithms that researchers continue to study systematically. Swanson has preserved her documentation and images as an art project exploring unexpected outputs of AI systems. Meanwhile, the broader scientific research on pattern stability in generative AI continues to evolve through peer-reviewed studies. Research teams at universities and AI labs continue to analyze the mathematical properties of latent space stability in diffusion models, developing new methods to understand and predict how these systems represent information. As AI image generation becomes increasingly mainstream, documented cases of pattern stability serve as important reminders that these systems don't operate according to human logic or expectations. They develop their own internal associations and representations based on statistical patterns in training data, creating a mathematical landscape that even their developers don't fully comprehend. In the rapidly evolving field of artificial intelligence, cases like Swanson's documentation of Loab highlight how these technologies can produce unexpected outputs that prompt further technical investigation. Research into pattern stability in generative AI is directly informing current commercial safeguards. Companies including Stability AI, Midjourney, and OpenAI have implemented various technical measures to prevent unintended content generation. These include content filters, training data curation, and algorithmic barriers designed to prevent certain types of outputs. Documentation from OpenAI's published research papers and technical blog posts indicates that their engineering teams are actively working on methods to better understand and control how their models navigate latent space. These technical documents emphasize that their safety work focuses not just on content filtering, but on developing systems with more predictable behavior. The fundamental question emerging from these documented patterns remains essential for AI research. As we create increasingly complex AI systems, how can we ensure we understand what patterns and associations they might develop? The mathematical complexity of neural networks with billions of parameters makes complete transparency challenging, which is why ongoing research in AI interpretability remains crucial. As we continue to integrate these powerful generative tools into our digital landscape, documented cases of unexpected pattern stability offer important opportunities for reflection. These aren't stories about fictional digital hauntings, but rather scientific investigations into the mathematical properties of systems we've created but don't yet fully understand. In the space between our instructions to these systems and their actual behavior lies a territory researchers are actively working to map through rigorous technical analysis. Thanks for tuning in, and thank you for listening. And until next time, stay curious, stay safe.